Okay, so to start with, remind me what's the symbol for temperature?
The symbol for temperature is T,
Capital, lowercase.
capital.
And what units do we usually use for temperature in this chemistry course?
We use Celsius and Kelvin.
Right. Now, for the material that we're working on heat and temperature change, we usually use degrees Celsius. But we saw that it doesn't really matter since we're focusing on temperature changes, so it would be the same in either units. So if you can feel the temperature of something going up, what does that mean on the molecular level?
It means that the molecules are moving around more.
Moving around more, moving around faster. That's correct. Now, we talked about how heat is not the same thing as temperature. What's the symbol for heat?
Heat is Q.
That's right. And what units do we usually use for heat in this course?
We can use joules or kilojoules.
That's right. We were mainly using joules last time, but you're right. We sometimes are going to use kilojoules. Do you remember what heat is?
It's the um, it's the energy that is transferred from a higher temperature to a lower temperature.
Substance. Okay, that's good. That's good that you remembered that's kind of a technical definition. So notice heat is a type of energy. That's why its units are in joules. And last time we talked about how for solving these problems we need to draw a heating curve. And the main substance that we were focusing on so far was water. In that heating curve, what concept goes on the horizontal axis?
The horizontal axis was heat.
And what concept goes on the vertical axis?
That was temperature.
That's right. Sounded like you weren't 100% confident about that. So that's important to have memorized because remember, we use the heating curve to solve the problems. Every problem, you need to draw a new heating curve, and you can't do that if you don't know what the axes are. So let's think about water again, and let's start with water that is, say, just to make up a number, let's say it starts at negative 20 degrees Celsius. Let's say I add a small amount of heat to that. If I add a small amount of heat to the water at 20 degrees Celsius, what will happen?
Well, since water it freezes at 0 degrees Celsius and you add a little bit of heat, you will be changing the temperature and you'll be increasing the temperature from negative 20 degrees to 0 degrees Celsius.
So at first we're going to raise the temperature. If we add enough heat, we can raise the temperature to 0 degrees Celsius. And I think good. Once we get to 0 degrees Celsius, what happens if we add a small extra amount of heat?
Then all the ice is going to melt and you'll have a phase change from ice to liquid water.
And what happens to the temperature during that phase change?
It stays the same.
That's right, it stays the same. Okay, good. So as you were noting, here we were in the solid ice phase, and here we're in the liquid water phase. Once we finish and get to this point, and we've melted all the ice, what would happen if we added a small extra amount of heat?
If you add a little bit of a small extra amount of heat to the liquid water, you're going to increase the temperature from 0 degrees Celsius to 100 degrees Celsius.
Yeah, now we're going to be raising the temperature, and that process will keep continuing until we get to 100 degrees. What happens if we get to this point and then we add even more heat, a small extra amount of heat?
Then the liquid water is going to undergo a phase change to vapor.
Good. And what happens to the temperature while that's happening?
The temperature will stay the same.
That's right. And then after it's completely vaporized, what happens if we add a little extra heat?
Then it's just going to increase the temperature.
Okay, excellent. So it's important to be able to draw this heating curve from memory. It's not, this isn't drawn to scale, but this shows all the different changes. So what do we call this movement from here to here?
That would be melting, or I think, what is it called? Fusion?
Yeah, that's called melting or fusion. And how about from here to here?
That would be freezing.
Or solidification. Good. How about from here to here?
That would be vaporization.
Or boiling? And from here to here?
That would be condensation.
That's right. That's the term that's probably the least familiar. Okay. And do you have those tables of constants with you that we were dealing with last time?
Yes, I do.
So what is the heat of fusion for water? What's the heat of fusion for water?
It's 334 joules per gram.
Good. 334 joules per gram. Now, let me ask you a question. What's the heat of freezing for water?
It's the same temperature. Or sorry, not same temperature. It's also 334 joules per gram.
That's right. Now, I was thinking about our last session, and I kind of changed my mind about the best way to deal with that. So I want to give you different advice than last time. Last time I told you to use the same number for the heat of fusion and for the heat of freezing, but actually I think things will be clearer if we use positive and negative signs. So in those terms, when you're melting, are you adding or releasing heat? If something's melting, is it absorbing or releasing heat?
It's absorbing heat.
So should the heat of fusion be positive or negative?
Should be positive.
So we could say the heat of fusion is really positive 334 joules per gram. So then what would you say is the heat of freezing?
The heat of freezing would be negative 334 joules per gram.
Yeah, I think that'll make it easier to solve the problems. So we should say this table really doesn't give us the heat of freezing, but we can figure it out. The heat of freezing is negative 334 because the way to freeze is to lose heat. So then what would be the heat of vaporization for water?
Heat of vaporization of water would be 2,260 joules per gram.
Good. And what would be the heat of condensation for water?
Negative 2,260 joules per gram.
Good. So I think that'll be a better way for us to be solving problems. What to do here? So that simplifies the equations. Last time I told you that the equations were Q equals mc delta T. But then when we were doing the phase change equation, I had to put this pesky plus or minus sign in front. And then the two equations kind of work differently. So I changed my mind about that. That's overcomplicating it. Why don't we just write both equations the same? But if you're melting or vaporizing, you'll plug in a positive number for the latent heat. And if you are condensing or freezing, you'll just plug in a negative number. I think that makes the two equations more symmetric. That makes us less likely to forget the right signs, hopefully, anyway. Okay, so we'll try that in some problems and see how it works. It shouldn't change things very much, but I think that's a way to avoid making mistakes with the signs. All right, so let's see. Oops, not what I wanted. Okay, so let's try this problem.
A 445 gram sample of ice at negative 58 degrees Celsius is heated until its temperature reaches 29 degrees Celsius. Find the change in heat content of the system. Well, we're given a mass, we're given an initial temperature and a final temperature. Find the heat change in the content, or find the heat change in heat content of the system. We can use Q equals mc delta T. Q is equal to 445 times the specific heat of ice, which is 2.01. We're going to multiply that by delta T, and delta T is equal to negative 29 minus negative 58. And that would be a positive 29. And then multiply all of that out and you get $25,939 joules, and you can divide that by 1,000 to get kilojoules. That's equal to 25.9, so 26 kilojoules.
Okay. So now let's make sure we're being systematic. The first step is to write a symbol for what the question's asking us. So what's a good symbol for what this question's asking?
Q.
And then the next step would be to get a prediction. What could you predict before you started doing any calculations here?
That Q would be positive because you're increasing the temperature from negative 58 to negative 29 degrees.
That's right. So that would be a good thing to do from the start. And then you had to use this 201. So I guess, how did you know to do that? Oh, because it was ice. So it's ice, you have to use this number, 2.01. So that seems like that was correct. And then you did your calculations. You have to be careful with the signs here. Negative 29 minus 58. But I think you did that correctly. 445 times 2.01 times negative 29 minus 58. 25,900. Good. And you were right, it makes sense to put into kilojoules, and that came out positive. That matched our prediction. Oh, something we should do to be more careful, though. So what's our initial position on the heating curve?
It is negative 58 degrees.
And what phase?
Ice.
So we could say we started here at negative 58 degrees initially. And what was the final point?
Negative 29 degrees Celsius.
And what phase?
Ice.
So it's good to put that in our diagram so that we can see which way we're moving. This problem was so easy, maybe you didn't feel that you needed the heating curve. But as the problems get harder, we saw last time that it's really helpful to build it into the curve. Okay, good. So looks like you're remembering what we went over last time. So let's try number 2.
A 152 gram sample of ice at negative 37 degrees Celsius is heated until it turns into liquid water at 0 degrees Celsius. Find the change in heat content of the system. Well, they're looking for Q, and then the temperature was at negative 37 and is heated until it turns into liquid water at 0 degrees Celsius. So Q is going to be positive. Now we can use Q equals mc delta T. Well, also, we're initially starting from negative 37 on the heat curve of water, and then we're heating it until it turns into liquid, into ice at 0 degrees Celsius. That's the first step. And then we add a little bit more energy until it turns into liquid. So it's going to be a phase change then from ice to liquid water, and that we would have to use Q equals ml. So Q equals mc delta T, 152 times ice, so that would be also 2.01, and then multiply that by negative 37 minus a negative, well, I guess final minus initial. So that would be positive 37 degrees. (152) times 2.01 times 37. That's equal to 11304. So that is equal to 11 kilojoules. Now Q equals ml. Since we're gaining heat, we have to and since we're actually melting it, we have to use the heat of fusion for water, I guess. And that would have to be Q equals ml. The mass is 152 grams, and we're going to use a positive 334 joules. So multiply that by 334 joules per gram, and then that's 152 times 334. That's equal to 50,768 joules, and that is equal to 50.7, so 51 kilojoules. And then we add that up, and that is equal to Q1. Q total is equal to Q1 plus Q2. So then 51 plus 11 is equal to 62 kilojoules.
Okay, so let's see. You started by writing down the symbol, and it sounded like you made a prediction, which was that Q would be positive. So that was good. And then you were using the heating curves. That's good. That allowed you to see that there was two separate steps. So this is the initial point, and this is the final point. One thing I would do as these problems get more complicated is write this equation then from the start. You use this equation eventually, but I think this would be a good way to organize your work from the start. We can say that Q total equals Q1 plus Q2, and then we can just plug everything into this one master equation. That's basically what you ended up doing anyway. And then you followed the advice I was just talking about of just saying that since this is fusion, we should plug in positive 334. And let's see, there seemed like there was some confusion here about these temperatures. At first, it sounded like you were doing negative 37 minus 0, but the final temperature for step 1 is 0, so it should be 0 minus 37. Should the heat exchange for step 1 be positive or negative?
Should be positive.
So that's the way to double check that you did things right. Did you actually get a positive number for this first step?
Yeah.
Yeah, so that's the way to double check that you're doing all those steps right. It's always good to double check that. So let's see. I guess you were using this number, 334, and you were using the specific heat of ice that we used before. Okay, good. So it looks like that came out. Well, let me check the answer. What did you get? 62. So if you actually look at the answer key, the answer that the answer key gives for this one is 6.23 times 10 to the 4th joules. Is that the same or different as what you got?
That's the same.
Yeah, okay. Except for rounding error, I guess. So that is, they put it in joules, so the way you put it is just fine. I would agree with you. It's actually more convenient to put this into kilojoules. Okay, good. So let's try number 3.
218 gram sample of steam at 121 degrees Celsius is cooled to ice at negative 14 degrees. Find the change in heat. So let's see, it goes from 121 to negative 14. So they're looking for Q, and it's going to be a negative number because we're losing heat. And then we start from 121 degrees Celsius. And then we lose energy until we become water vapor we lose enough energy to get back to 100 degrees, get down to 100 degrees Celsius. So that's the first step, and that is equal to Q equals MC delta T. And then the second step is we lose a little bit of more energy, and we turn water vapor to liquid water. So that is equal to Q is equal to ML. And then what we do is we're losing a little bit of more energy, and we are getting down to 0 degrees Celsius. So we're going to use Q equals MC delta T again for our third equation. And also Q total is equal to the sum of all Q's. And then the fourth one is, since we have liquid at 0, we're going to lose a little bit of energy and go from liquid to ice. So that is equal to Q is equal to ML, where liquid goes to ice. And then the last one is changing the temperature from 0 to negative 14, where Q is equal to MC delta T. Package, and now Q equal to MC delta T, where Q is equal to 218 grams times the specific heat of ice, or not ice, but steam is 2.01. And then multiply that by the delta T, where you have 121, or where it goes from 121 degrees minus or to 100. So that would be 100 minus 121, and that's positive 21. 100 degrees. Negative 121 degrees Celsius, and then that would be 218 times 2.01 times negative 21. That is equal to negative 9,202 joules. Second equation, Q equals ml. And this is where the liquid, or where the gas turns to a liquid. So Q is equal to 218 times the heat of condensation for water, and that's a negative 2,260 joules per gram. So 218 times 2, and I get a negative 49,000 492,680 joules. The third equation is where we use Q equals MCAT, where the temperature of the liquid goes to from 100 degrees C to 0 degrees C, where Q is equal to 218 times the specific heat of liquid water, which is 4.184, times negative 100, 218 that gives me negative 91,000, 91,211 joules. The fourth equation would be Q equals ml, where the liquid turns to ice. And that means Q is equal to 218. And then since it's going from liquid to ice, that'd be freezing. So it would be negative 334 joules per gram. That is equal to 218. That is equal to negative 72,812 joules. And then the last equation we use will be Q equals MCAT, where the ice goes from 0 degrees Celsius to negative 14 degrees Celsius, where Q is equal to 218 times the specific heat of ice, which is 2.01, times the temperature change, which is negative 14. And then that is 218. That is equal to negative 424 joules. Q total is equal to let's see, negative 92,000, or sorry, negative 9,202.
What did you get for this last term here?
Negative 14.
Check that again.
Oh, I'm sorry.
Oh, for the
The
whole
answer
multiplication, yeah. 218 times 2.01 times negative 14. What did that come out to be?
218 times 2.01 times negative 14. Oh, whoops. 6,100 or 6,134 joules.
Is that what you got the first time?
No, the second time.
Okay. What went wrong the first time? Did you just enter it wrong in the calculator?
I guess so.
Okay. All right.
So now Q total is equal to the sum of all of them, which will be that is equal to 671,410 joules. And then, or negative, sorry, negative 671,408 joules.
Okay. And what did you use as the last term here?
Negative 6,134.52.
Okay. I think I got something different than you. I don't think that was just a rounding mistake. So let's go through that again. So what's the calculation you did on that last step?
218 times 2.01.
Oh, you did all these calculations all over again? It seems like you could just use
Oh,
these
you mean
numbers.
the total Q?
Yeah. What's the calculation you
Uh,
did? So this number is correct. This number looks right. Tell me again the calculation you did to find the total Q.
Total Q is the sum of all the Q's, so negative 9,202
Good.
plus a negative 492,680
Good.
plus a negative 91,211
Good. Whoops.
plus the negative
Mm-hmm.
plus a negative 72,812,
Good.
plus a negative 6,134,
Oh, looks like maybe I was the one that made the mistake. Okay, so what answer did you get?
negative 671,409 joules.
Now I'm pretty close to you, so I guess this is just rounding error. So you got negative 670,000 approximately, huh? Let's see, where did I go wrong? 9202,492,680,91. Oh, I see what I did wrong. All right. Okay. So what's the answer to the question?
Negative 671,409 joules.
Good. I think it would be convenient to put that into kilojoules.
It would be negative 671 kilojoules.
Or I got negative 672. Okay. Now let's check. That matches your prediction. Now, ahead of time, would you have predicted that the first term would be positive or negative?
The first term would be
How
negative.
about the second term? And the
Negative.
third term? And the
Negative.
fourth term? And the
Negative.
fifth term? And did
Negative.
they all come out negative? Yeah,
Yeah.
that's a good thing to double check though, because we know it's so easy to make a math mistake and have something come out with the wrong sign. So it's good to check all of these to make sure they're really coming out the way you would have predicted. So is this object gaining or losing heat?
It's losing it.
When did it lose the most heat? In which step?
It lost most heat in step 2, where the gas phase goes to the liquid phase.
That's right. So that's an interesting point. Notice that the heat exchange is most significant when water is vaporizing or condensing. Heat exchange is most significant when water is vaporizing or condensing. It takes a lot of heat to vaporize water, and it also takes a lot of, you have to release a lot of heat to condense water. That's a lot bigger than any of the other terms here. That's an interesting fact about water, and you can see why, because this heat of vaporization or heat of condensation is so big, much bigger than for other normal substances, and from the bottom of the table here. So that's an important fact about water. Okay, so I think you did a good job of being systematic here. Notice this is where the heating curve is really necessary. The heating curve is really helpful here because there's so many steps. It's hard to keep track of them without this. So I think you did a good job here of being systematic. It looks like if this was a test question, you wouldn't have gotten full credit because there was one careless mistake with one of these terms here. So notice how it's really important to double check each step if there's many, many steps here so that you can get all the credit. But I think that was the only mistake that we made. Okay, good. The most important thing you did here is you remembered to put in negative numbers for the heat of condensation and the heat of freezing. That was that new kind of approach that I was just discussing with you before. I think that's better than the way we did it yesterday. So that's the part that people are most likely to forget. Most students would put in positive 334 or positive 2260. So it's really good that you remembered that. You should note that in your notes for future reference. So does water gain or lose heat when it's vaporizing? When water vaporizes,
Gains it.
yeah, it gains heat. That is, it absorbs heat from its surroundings. Why do people sweat?
To cool off.
But why does sweating cool you off?
Because water water has a high heat capacity, so as a I guess as a person is heating up and the sweat is on his skin, it's absorbing that heat.
Let's see here. They're probably actually that might be part of the story. That is part of the story. I suppose it's hard for the water absorbs a lot of heat when its temperature is rising. But the key point, the thing that's most important, is the main purpose of sweat is to you want the sweat to vaporize. Because what happens when the sweat vaporizes? What happens to the sweat when it vaporizes? Does it absorb or release heat?
It absorbs heat.
It absorbs heat. Who does it absorb the heat from? The rest of your body. It absorbs the heat from your skin. So do you see how that would leave your skin and your body cooler then?
Yeah.
So that's the main purpose of sweating. The main purpose of sweating is you want the sweat to vaporize. because when it vaporizes, it's absorbing heat from your body and taking that heat away into the atmosphere. That's why it's so uncomfortable if you're in a place that's very humid. If you're in a place that's very humid, there's already so much water in the air that the sweat can't vaporize very well. The sweat just stays on your skin, and that defeats the whole purpose and makes people feel really uncomfortable. Why do dogs pant?
Well, they can't sweat, so instead they pant to release some of the water vapor.
Okay, yeah. So I guess they don't have sweat glands. They can't sweat from their skin. The whole point of panting is it exposes their slobbery tongue, right? The tongue is really wet, it has water on it. What do they want to have? What is supposed to happen to the water on the dog's tongue? How does that water on the dog's tongue cool the dog off?
It
Yeah, it
evaporates.
evaporates, and when it does that, it absorbs heat and takes the heat away. So probably most dogs are not aware of this, but the reason that they pant is to expose those wet tongues to the atmosphere so the water can vaporize and take the heat away. That's all based on the idea that we were just talking about, that vaporization or condensation involves a very big heat exchange. There's a big heat exchange for vaporizing or condensing. So that's why that's effective. Okay, good. All right, well, that's good that you got that right. That's a pretty complicated question. So let's move on to a different type of question here. So yeah, let's erase this. Okay. Now this problem is related to the ones we did before, but it's also a little different. So let's see if we can figure out how to adapt our methods to try this. Give this a shot.
A sample of water starts at negative 50 degrees C and absorbs
Oh, I'm sorry.
50,000
Excuse me.
joules of heat, ending up as vapors at 110 degrees C. Find the mass of the sample.
Yeah, but let's just say it starts at positive 50 degrees C. Not negative 50 here, but positive 50.
50 degrees, so... Well, it's ending up as vapors at 110. So we're looking for the mass, so we're looking for M. Now we know that it starts out as a liquid at 50 degrees Celsius. It absorbs a certain amount of energy, and then it's going to reach 100 degrees Celsius where it'll still be zero. So I guess one equation we could use is equal to Q is equal to mc delta T, where the initial temperature of 50 degrees C goes to 100 degrees Celsius. And then at 100 degrees Celsius, the liquid is going to turn into vapor. So we would use Q equals ml. Oh, actually, never mind. Well, wait a minute. And then in the third step is going to go from vapor at 100 degrees to 110 degrees. So that's just a temperature change. So that's Q equals mc delta T, where the gas at 100 degrees C goes to 110 degrees C. Now we know that it absorbed 50,000 joules, so our total Q is equal to 50,000. And in the first equation, mc delta T, we know that the specific heat of water is 4.184 times the temperature change, which is 100 minus 50, which is 50 degrees. And we know that Q is going to be positive because it's gaining energy. And I guess that would equal 50,000. Because then we would figure out the mass of the liquid. So let's see. 4.184 times 50 degrees temperature change. That is equal to 209 m, and then 50,000 divided by 209. That is equal to that is equal to 239 grams. Now, in the second one, Q is equal to ml, so that means 50,000 joules is equal to m and L, which since it's going from liquid to gas, that would mean that it is it's vaporizing, so that's 2,200 2,226 joules. So 50,000 joules is equal to m times 2,260. Divide both sides. So 50,000. Divide that by 2,260. That is equal to 22 grams. And then Q3 is going from gas at 100 to
Now, let me
gas at
interrupt you there.
110.
So you have this equation for Q1 and this expression for Q2. Is the mass that goes through step 1, so forget about the calculations that you did and think about common sense. Should the mass that goes through step 1 be the same or different as the mass that's going through step 2?
It should be the same.
Because it's the same sample. And should that be the same or different as this mass that's going through step 3?
It should be the same.
Now think about the method that you've been using to solve this problem. You've just figured out the mass from step 1 and the mass from step 2. Did you get those two masses to be the same or different?
They were different.
Which means there must be a mistake in that method. We must be making a mistake because the masses are supposed to be the same, not different. So the problem is, what does this 50,000 represent? What would be a good symbol for the 50,000?
Q. Q total.
Q total. That's what you said. That's right. But you didn't quite use that to solve the problem. But then you actually set 50,000 equal to Q1. You actually set 50,000 equal to Q1. You did 50,000 equals Q1, but that's incorrect. The 50,000 is not just the heat from step 1. Right?
Right.
So we have these variables, Q1, Q2, Q3, and Q total. In order to solve the problem, we need an equation. What would be an equation that could relate these 4 variables? What's an equation that would relate these 4 variables?
Okay, so then it would be Q total is equal to M times the product of specific heat and change in temperature plus the latent heat plus the product of the third specific heat and change in temperature, and then you divide Q total by the addition of all those numbers, and you divide it, and then that'll give you the grams.
Okay, all right. That sounds like you're on the right track. Now, just to be systematic, what's the equation that relates these 4 variables? Q total, Q1, Q2, and Q3. If I was going to write down an equation with those 4 variables, what would be the equation I write down?
Q total equals Q1, Q2, Q3.
Like this?
Q1 plus Q2 plus Q3.
Okay, that's right. So this should have been the equation that we started with. This is the equation that we started with. Once you see it, this should be common sense. If you add up the heats from each of the individual steps, that's Q total. If you think about it, that's the same equation that we did the previous problems with. That's the same equation we used as for the previous problems. The total Q is the sum of the individual Qs. Then you can plug in 50,000 for the total Q. And on the right-hand side, you can plug in each of these individual terms. So the mistake that you were making was that you were trying to set each term separately equal to 50,000. You knew that this was the total heat, but you weren't really using that to solve the problem. Okay, so now that gives us this equation here. So now what? What's the next step now? What do we write down next for solving the problem?
That would be plus ML, so that would be plus what is it? 2,260, and then plus 2.01 times 10.
So what's the equation you have written down now?
50,000 is equal to M times 4.184 times 100 minus 50 plus 2,260 plus 2.01 times 110 minus 100.
Plus 2.01 times. So is this what you have written down?
Yeah.
Okay. Now, if that's actually what you have written down, it sounds like you lost the m's from these two terms.
Oh. Um. Yeah, I would have to add the m's.
Yeah. So basically, we're just substituting into this equation. We're just substituting into this equation. What do we substitute for m? Just m, because we don't know it yet. And what do we substitute for m here? Well, just another m. So what you should have had written down, I think, is this. Like this? Okay. And should this be positive 2,260 or negative?
Positive,
How do you know?
because it's vaporizing.
That's right. Okay, so that's an important thing to think about. So now is this the equation you have down?
Yeah.
Okay, so now what would you write down next?
Well, now we can factor out an m, and I guess that would be 50,000 joules is equal to 3m times 4.184 times 100 minus 50 plus 2,260 plus 2.01 times 110 minus 100.
Is this what you wrote?
3m times 4.184 times all of that.
So this is what you wrote?
Yeah.
Let's do a little algebra review here. What can you can factor out an x from here. So how would you rewrite this if you factored out an x?
X times 4 plus 5y plus 6z.
So you wouldn't factor out a 3x, would you?
Oh,
You wouldn't
no,
factor
you
out
wouldn't.
3x, you just factor out x. Because 3 is not the common term, x is the common term. So there looks like there was a mistake here. What should this have really been?
1.
Yeah, or just m. How did you get confused there? Well, what's m plus m plus m?
3m.
Yeah, so if you were just adding the m's directly, then you would have a 3m. But we're not adding the m's directly here, we're factoring from each term. You can see that because if you tried to use the distributive law, you wouldn't get back to where you started. If you did 3m times this, it wouldn't take you back to the original term. Anytime you factor, it's good to try to use the distributive law to make sure you did it correctly. So it looks like there was an algebra mistake on that term. This should just be an m. Okay, so now what? You're working on that?
Yeah.
Okay.
So now we have 50,000 is equal to m times 209.209 plus 2,260 plus 20, and then I get
Let me catch up with you. So what was your first term?
209.
I didn't get that. How'd you get that 209?
let's see, 4 point. Oops, I got 167.36. So it's actually 167.
What's the calculation you just did?
4.184.
Oh, so you're doing it right and I'm doing it wrong. I got the wrong thing written down. 4.184. 4.184. Let me try again. 4.184 times 50. Okay, tell me again. What did you get from that?
209.2.
All right, yeah, you were right. And then plus what?
Plus 2,260.
Good. And then
Plus 20.
okay, good. Now what?
Now just divide 50,000 by 2,489. And then we get M is equal to 20.08, 20 grams.
What was your answer again?
20 grams.
Approximately 20 grams. Okay, good. All right, so that problem gave us some difficulty. Now that we've done it, you should compare this to the previous examples. I erased the previous examples, but you should go back in your notes and you should see that the method here was almost identical to the previous problems. We still used this basic equation, this obvious equation that the Q total is the sum of the individual Qs. The only difference is that this problem involved more algebra because we were solving for a variable that was inside of the equation rather than just the left-hand side. So the biggest problem we had here is that I think at first you were trying to set the 50,000 equal to each of the individual heats, but it should be equal to the total heat. They add up to this heat. And also we had some algebra problems as we were working through that. So that's something to be careful with. You don't have to factor out an M at this step if you don't want to. You could have just simplified each term separately. Either way is okay. Okay, so this is another popular type of problem on exams that has a little bit more algebra in it. We had some trouble with this, so you should definitely try that problem again. But you can still see how the heating curve is really helpful for summarizing that. Does that problem make sense now?
Yes.
Better, because I'm already erasing it. You did get off to a good start on that last problem because you started by writing down the symbol for what the question was asking you. So you were clear from the start that it was asking for mass. That is a good way to start with the problem. Let's try number 7.
And going from ice to negative 34 steam at 138, a sample of water absorbed 1.41 times 10 to the 5 joules. Find the mass of the sample. Well, we're looking for M. And we know that we have ice from negative 34, and it's going to gain heat because it's going to 138. So it's going to go from negative 34 to 0 degrees. And that was where you would use Q equals MC delta T. Second one, you have ice at 0 degrees C that goes to liquid at 0 degrees C. That is equal to Q is equal to ml. Then the liquid at 0 degrees C is going to go to 100 degrees C. So that's Q is equal to mc delta T. And then the liquid is going to go to a gas. And that's Q is equal to ml. And then gas at 100 degrees C is going to go to gas at 138 degrees C. So that's Q is equal to mc delta T. Now Q total is equal to mc1 delta T 1 plus ml plus mc2 delta T2 plus m sub 2 L sub 2 plus mc3 delta T3. So 141 times 10 to the 5. That's 141,000 joules is equal to m times, since it's at ice, the C would be 2.01 times delta T, which would be negative 34 minus 0, which is negative 34. I'm sorry, it'd be 0 minus negative 34, so it's positive 34. Plus m sub L, where it's melting from ice to liquid, so it'd be m times 334 plus m times the specific heat of water, 4.184, times the change in temperature, which is 100 minus 0, which is 100, plus m times L, which would be the heat of vaporization of water, which is 2,260, plus m times a gas, which is 2.01, times the change in temperature, which is 38. Now we can factor out an m, and we get 141,000 is equal to m, and then 2.01 times 34 plus 334 plus 4.184 times 100 plus 2,260 plus 2.01 times 38. So 2.01 times 34 is equal to 68.34 plus 334 plus 4.184 times 100, which is equal to 418.4 plus 2,260 plus 76.38. Now we add those all together. And we get 141,000 is equal to M times 3,157. We get 45 grams.
Approximately. Okay, good. So what was Q total that you wrote down here?
141,000.
1.41 times 10 to the fifth. So if we move the decimal point 5 places to the right, that's 1, 2, 3, 4, 5. Okay, good. Yeah, I guess I was leaving out a 0 before. So now I think what you said was correct. I was writing the wrong thing. So then we get 45 grams. Okay. All right, so that problem went better than the one before. So now what I'm trying to do is write down what I think is the most organized way to do this. What's the first equation we should write down? Excuse me, after you do the heating curve and figure out the steps, the first equation you write down should be this. It sounds like you might not have written this down explicitly. I think it's a good idea to write this down explicitly because it shows that you're really understanding conceptually what's happening in the problem. We have a total heat and we're breaking it into 5 different steps. So I think this would be a good equation to write down at the start once you identify all the different steps. But then I think you did a good job of plugging in. Do we expect the heat exchange 1 to be positive or negative?
Positive.
How about 2?
Positive.
In fact, we expect them all to be positive. Did they all come out positive?
Yes.
Yeah, you can see all these terms here are positive and they're being multiplied by a positive mass. Remember, it's always good to double check that because it's easy to make mistakes with the signs. Okay, so now we're done with this specific type of problem. So what type of problem is it that we've just done here? We've just been working on problems that involve one substance. We've been doing one substance or one sample problems. And now we have to move on to when there's 2 substances. So let's try and do that. I guess I'll erase this first. Okay, so now we're going to try to move on to 2 substance problems. Let's say you have 2 substances, and one of them here starts at 50 degrees Celsius, and the other one starts at 30 degrees Celsius. What's going to happen? In qualitative terms, what will happen here if we have two substances touching each other? Two substances touching each other, one that's at 50 degrees Celsius and one that's at 30 degrees Celsius.
They're going to reach a temperature equilibrium.
That's right. So which way will the heat be flowing?
To the right.
Good. And you're right, eventually they're going to end, if we wait long enough, they'll end in thermal equilibrium. What does thermal equilibrium mean?
Equilibrium in temperature.
Yeah, what does equilibrium in temperature mean? Equal temperatures. So they're going to end in thermal equilibrium. We don't know what the final temperature is going to be. It depends on the exact nature of the samples. But for example, they might end up at 45 degrees Celsius and 30. And if this ends up at 45 degrees Celsius, what temperature will the right-hand side end up at?
45.
Yeah, I just made that number up. But we know for sure the temperature has to be between where and where?
Between 30 and 50.
That's right. Now, let's call this side number 1 and this side number 2. So is Q1, let's do Q2. Is Q2 going to be positive or negative?
Q2 will be positive.
So I'll just make up a number. Suppose that Q2 is 100 joules, positive 100 joules. If Q2 is positive 100 joules, what would Q1 be?
Negative 100 joules.
That's right. How do you know that? Because if this substance is absorbing 100 joules of heat, it must have gotten it from the left-hand side. So the other side must be releasing 100 joules of heat. In these problems, we assume that there's no heat exchange with the outside environment. We assume we're doing an insulated experiment with no heat exchange with the outside environment, so any heat that goes into sample 2 has to come from sample 1. Now, the problems we're going to do are going to have lots of heat exchanges. A whole bunch of heat exchanges. But if you add up all the different heat exchanges in a two-sample problem, what are they going to add up to?
Q total.
But what will Q total be? If we end up at what will Q total be in this multi-sample problem? If we add up all the heat exchange from all the different substances.
It'll be at could you repeat that?
What will Q total be if we have more than one substance?
Q total will be, it'll be at equilibrium, so in this case Q1 plus Q2 will mean this equal to 0 joules.
Okay, yeah. Now, it's not really because we're going to thermal equilibrium. Even if we didn't go to thermal equilibrium, they would still add up to 0. After all, what was Q1 plus Q2 for this little example?
0.
Yeah, so in general, remember that I said a second ago that we're assuming that this is thermally insulated and that there's no heat exchange with the environment. That means that all the heat that is released by one of the samples has to be absorbed by another sample. So if we add up all the different heats, they're going to have to add up to 0. So this is going to be our key problem, our key equation for solving these problems. Our key equation now, maybe we can write it like this. The sum of the individual Q's is always going to add up to be 0 for a multi-sample problem. When there's multiple substances, the sum of the heats is going to add up to 0. Because any of the heat that's released by one substance has to be absorbed by another substance. So this is going to be the key for solving these problems. Notice how this is different from when we did a one-sample problem. When there was only one sample, if the sample was absorbing heat, we didn't say where that heat was coming from. Or if the sample was releasing heat, we didn't say who it was releasing it to. So in those one-sample problems, the total heat didn't have to add up to 0, because there was only one substance. But if you have multiple substances that you assume are insulated from the environment, then all the heat that's lost by one substance has to be gained by the other, and the total heats have to add up to 0. So that's going to be our key equation for solving these types of problems. All right. 1 second. Okay, have that written down?
Yeah.
All right, so let's go through this problem together. So the first step would be to identify what the question is asking us for. So what would be a good symbol for what this question is asking?
TF.
That's right. Okay, so now this is going to be more difficult than before. Is this a one sample problem or a multi-sample problem?
It's multi-sample.
Yeah, what are the two samples?
Gold and water.
So we need more than one heating curve. We don't just need the heating curve for water. Now we also need a heating curve for the gold. Now what's that heating curve going to look like? Well, there's something that's weird about water. The thing that's weird about water is that it can take any of three phases at ordinary temperatures. In ordinary life, you encounter liquid water all the time. You encounter solid water, say in your freezer. You encounter water vapor, say the steam when you boil water on the stove. So in ordinary life, water can take on any of these three phases. But if you think about it, that's very unusual. Most substances only take on one phase at ordinary temperatures. For example, what phase is say gold usually in?
Solid.
Yeah, you're never going to see liquid gold at ordinary temperatures. Or what phase is oxygen usually in?
Could you say that again?
What phase is oxygen usually in?
Gas.
Yeah, you're never going to see liquid oxygen at ordinary temperatures. So the phase diagram for other substances looks different than for water. It just looks like this. We don't expect the gold to undergo a phase change at any ordinary temperature. So I don't need to put in a phase change region here. I'll just say this is what the curve looks like for solid gold. So this is the heating curve for solid gold. It's not going to go through any phase changes. So what is our initial point here? Well, our initial point is that we have the 100 grams of gold at 300 degrees Celsius. So here's the initial point for the gold. 300 degrees Celsius. And what's the initial point for the water?
20 degrees Celsius.
And what phase is it in? What phase would the water be in initially?
It'll be at liquid. It'll be actually at Yeah, it'll be at liquid.
They didn't tell us that, but they don't have to, because we know that at 20 degrees Celsius, water is in liquid phase. Now, what do you know about the final temperature? What can you predict about the final temperature? What can you predict? Yeah.
The final temperature will be somewhere in between 300 and 20 degrees.
That's right. So, and what do you predict we know that the final temperature of the water will be the same as the final temperature as the gold. In this problem, even though they didn't say so, we should assume that we're going to wait long enough till we get to thermal equilibrium. But now we have a little bit of a difficulty because we don't know whether the final temperature will end up. So what's going to happen to the liquid water?
It's going to evaporate most likely.
Possibly. We know for sure it's going to get hotter. But if we end up here, it'll still end up in the liquid phase. If we end up here, it'll end up partially vaporized. And if we end up here, it'll end up completely vaporized. So these problems are actually a lot more difficult than before because we don't know which of these three regions we're going to end up in. However, who do you expect to change temperature more, the gold or the water? Who is it easier?
The gold.
Yeah. Do you remember, is it easy or hard to change the temperature of water?
Relative to gold, it's a lot harder.
Yeah. In fact, remember, it's harder to change the temperature of water than pretty much any ordinary substance. It's harder to change the temperature of water than almost any ordinary substance. So, as a result of that, our best guess is that we're actually going to end up, say, here. It's the gold that's going to change a lot in temperature, and the water probably won't change in temperature enough to vaporize. The water probably won't change in temperature enough to vaporize because it's so much harder to change the temperature of water than of gold. Here's the other reason. Do we have more gold here or more water?
We have more gold. Or sorry, we have more water actually.
In fact, we have a lot more water, right? Since we have a lot more water, again, it's going to be much harder to change the temperature of the water than the gold. So if you only put, say, a speck of gold into the water, that's probably not going to give it enough heat to vaporize it. So for both those reasons, our best guess is that we're going to end up here. But that's really just a guess. These problems can be difficult because if your first guess doesn't work, you have to try the problem again. Okay, so let's go ahead then and try solving this problem. So what are the heat exchanges that we have? Well, we're going to have Q1, this heat exchange over here for the water, if our guess is right, and Q2, this heat exchange for the gold. And notice these two temperatures end up being the same. So what's the first equation that we write down? Well, what can we say about Q1 plus Q2?
Well, since you have liquid water at 20 degrees, and it most likely isn't going to go to a gaseous phase, so we can say Q is equal to mc delta T because you're only increasing the temperature.
Okay, that's good. That wasn't quite what I was asking. What can we say about Q1 plus Q2? What's an equation we can write about Q1 and Q2? We need to start the problem with an equation.
Q total is equal to mc delta T plus ml.
Okay, yeah, that is a true equation. However, that introduced a new variable Q total. What could we say? What's an equation you could write just about Q1 and Q2 with no other variables? What's an equation you could write just about Q1 and Q2 with no other variables?
MC.
Well, those are other variables. What's an equation you could write about just Q1 and Q2, just those variables with no other variables?
Q total equals Q1 plus Q2.
Good. But what's Q total?
Q total in this case.
With no other variables.
0.
That's right. How do you know?
Because the same amount of energy is going to be transferred from one substance to the other substance. Therefore, they're going to be in thermal equilibrium.
Okay, yeah. Now, the first thing you said was correct. It's true they're going to be in thermal equilibrium, but that's not why the heats add up to 0. Even if we didn't wait until their temperatures were the same. This was the argument we were giving a few minutes ago. Remember that if we assume that these two things are insulated from the environment, then any heat that's released from one has to go to the other one, whether they end up in equilibrium or not. So what's the equation we can write that only involves Q1 and Q2?
Q total is equal to Q1 plus Q2.
That's still not quite right because Q total is a new variable. What's the equation we could write that only involves Q1 and Q2?
Uh, that only equation that only. Oh, Q1 is equal to Q2. No, sorry.
We just want to apply the ideas we were just talking about.
0 is equal to Q1 plus Q2.
Okay, that's right. It looks like that's not really very intuitive for you, so it's important to go back and think about that. Remember, this was the equation we were talking about when we were preparing for the two sample problems? When we were preparing for the two sample problems, remember we said that the basic equation is that the sum of the heats always adds up to 0. For two sample problems, or for multi-sample problems, this is the basic equation. For multi-sample problems, the sum of all the heats always adds up to 0 because any heat that is absorbed by one substance must have come from another substance. So this is the first equation to write down. It's always good to start with a very general equation and then plug in. All right, now we can go ahead and plug in the individual terms. So what would we plug in for Q2? How would we calculate Q2?
So 0 is equal to mc delta T plus ml.
Now we need to use different symbols here because these two masses, are these two masses the same or different?
They're different.
So we can't use the same m for both of those. These are going to add up to 0. Okay, so now this is the next equation that we have written down. And what do we plug in for m1?
M1 will be the mass of water,
Yeah, what's that?
which is equal to 250 grams times specific heat capacity of water, which is 4.184, times the change in temperature, which is what we're trying to figure out. So that would be TF minus TI.
What could you plug in for Ti?
TI would be 20 degrees.
Yes, that's right, which we can see from here because we're talking about the water. So it's good that you were thinking in terms of TF minus TI, but we can plug in a specific number for that. And now we need to plug in for this term.
And now we would say plus M2 of L2, but that would be of the gold. So that would be 10 grams times the specific heat of gold, which is, I think, 0.129.
Do you have that memorized? Or what?
Yeah, 0.129.
You actually have that memorized? Or did you
I'm
look
sorry?
it up? I'm sorry, I'm just curious. Do you have that memorized or did you look it up?
I looked at the table.
Okay, good. You just looked at it fast. All right, so let's see. Where was I? I have to check that. So, what's that? Is gold in this table? Here it is. So specific heat for gold. This is the table your instructor gives you, right? So I guess that. So 0.129? Yeah, it looks like you're right. 0.12.
And that is all equal to 0. So what we can do now is we can take...
I'm sorry. Let me interrupt you. Wait. Is this is what you have written down? I guess we were getting confused here. Why did we write ML here? I don't know why we wrote that. One of us must have made a mistake. So what's happening? What's going to happen to the gold? Is it going to change phase or change temperature?
Change temperature.
Yes. Why did we write this? I don't know. I guess we were getting confused. All right. We better go back and fix that. That was the whole point I was making to you before. Remember, I was talking about how most substances don't change phase at ordinary temperatures. You're never going to change the phase of gold at ordinary temperatures. You're not going to melt gold ordinarily in your kitchen. So, what we should have written down for Q2 was M2 C2 delta T2. So let's go back and try again. What do we plug in for M2?
It would be 10 grams times 0.129 times TF minus 300.
Good. And it's good that you're being careful to do T final minus T initial. That's really important on these problems. And that all equals what? 0. Okay. All right, now I think we have it set up correctly. So now what? What would be the next equation you would write down?
So 0 is then equal to 2.50 times 4.184, which is 1046 times TF minus 20 plus 10 times 0.129. That is equal to 1.29 times TF minus 300. Now we can distribute, so 0 is equal to 1046 TF minus 20,920 plus 1.29 TF minus 301.29.
What was that last number?
301 point, 301.
What was the calculation you just did?
300 times 1 point, oh no, sorry, it's 0.129, so it actually should be 0.129 TF, and then 0.129, and that's 38.7.
38.7. Okay, yeah. So I guess I was writing down the wrong specific heat. It should have been 0.129. Okay, good. Then what? The student and I both made a mistake, and we didn't catch that mistake, so we ended up getting the wrong answer to the problem without realizing it. So I thought that for purposes of the YouTube video, I would go back and finish the problem correctly. So here's what we should have done. We should have said that 10 times 1.29 is 1.29. So here's our next version of the equation that we're trying to solve. I think we wrote this originally, but then for some reason we went back and wrote this number as 0.129. We forgot that we had to multiply by the mass of 10. So anyway, now I'll go back and try to do the problem correctly. So using the distributive rule, this would be 1046 TF minus 20 times 146. 20 times 1046 is 20,920. And now we use the distributive law again. So this should be 1.29 times TF. Because here we had to multiply 10 times 0.129. And then it would be 1.29 times 300, which is 387. So again, the mistake we made was that we forgot that we were multiplying the 0.129 times the mass of 10. So that should have given us 1.29 at this point. Instead, for some reason, we went back and wrote 0.129, which was wrong. Anyway, I think I'm doing it correctly now. Now we need to collect terms. 1046 TF plus 1.29 TF is 1047.29 TF. And then negative 20,920 minus 387 is negative 21,307. Now we add 21,307 to both sides, and that gives us 1,407.29 TF equals 21,307. Then we divide both sides by 1,047.29. And TF is 21,307 divided by 1,047.29. 20.34 degrees. So that's our answer. That matches our original prediction. Remember that originally we were predicting that the answer would be between 20 and 300, and this did come out to be in that region. You might be surprised by this because it's only a little bit bigger than 20 degrees. This is only a little bigger than 20 degrees, but remember the reason for that is that it's much harder to change the temperature of water than of gold. Notice that here the specific heat of the water is 4.184, which is much bigger than the specific heat of the gold, which is 0.129. It's much harder to change the temperature of water than of gold. And on top of that, we have way more water than gold, which again makes it much harder to change the temperature of the water. So with this particular setup, the water increased in temperature, but only by a small amount. Now, another complication here is that, remember, we were only kind of guessing that the final point would be here. The final point could have come out to be here or here as well, so we have to check whether our guess was correct. How can we check that our guess was correct? Well, our guess is correct if the final temperature comes out to be between 20 and 100 degrees. We were guessing that the final temperature would be between 20 and 100 degrees because, again, we know it's hard to change the temperature of a large amount of water. And we can tell that our guess was correct because the temperature did come out to be between 20 and 100 degrees. For the sake of argument, we had done the problem, and suppose that we had tried solving the problem this way, and suppose we had gotten that the TF was equal to, say, 120 degrees. That's not what happened, but just suppose that happened. What would that tell you? Well, this is a little bit subtle, but what this would mean that we'd made a wrong guess. Remember, we were guessing that the final point would be in the liquid water phase. If the final temperature had come out to be 120, that would just tell us that our original guess was incorrect. We didn't end up in the liquid water phase, and that would mean that we would have to do the problem all over again with a different guess. Then we would have to do the problem all over again with a different guess. Then it would get kind of complicated because there's still there's two different guesses you could make. You could guess that you're going to end up somewhere in this horizontal region, or you could guess that you'd end up somewhere in the vapor region. If you take a guess and then the final temperature is not consistent with that guess, that means you have to do the whole problem all over again with a different guess. We didn't actually end up doing any problems like that, though, in this tutoring session, because I think most chemistry courses are not going to give you problems that hard. Probably most chemistry courses are just going to give you problems, two sample problems, where you stay in the liquid water phase. I think that most chemistry courses are only going to give you problems where the water stays in the liquid phase. So we didn't end up doing any harder problems where the water changes phase in our tutoring session. Water, in most chemistry courses, the water is going to end up staying in the liquid phase. In most courses, when you're doing two sample problems that involve liquid water, the water will probably end up staying in the liquid phase, and you can use that guess to solve the two sample problem. Now, you should certainly know that that's not true for one sample problems. If you've been watching the earlier parts of this video series, you've seen many one sample problems where the water does change phase. So I hope I'm making that clear. In one sample problems, it's very common for water to change phase. But I think that in most courses, If you're doing a two-sample problem, the water probably won't change phase. And those are the types of problems that we did in these videos anyway. So that reminds me to make sure that you're reminding yourself. I hope that it's clear to you that now in these videos we've done two different types of problems. Most of the problems that we've done up to now have been one sample problems. We did a lot of one sample problems, and now we're just starting to learn how to do two sample problems. This is the key equation for a two sample problem. As I tried to explain earlier, this is not the equation you would use for a one sample problem. But in a two sample problem, you can assume that the sum of the heats adds up to 0. So try not to confuse the method we used for the earlier one sample problems with this new equation for two sample problems. Hopefully I'll clarify that again later in these videos. But you should still try to keep using the heating curve approach. Try to lay out all the different heat exchange steps before you write down your equation. And you can see that for these two sample problems, you will often need two different heating curves, because if you're using two different types of substances, they have two different curves. The curve for water looks like this because it can change phase at ordinary temperatures, but the curve for gold looks like this because, and the curve for most other substances looks like this because most other substances don't change phase at ordinary temperatures. I thought of one more thing I wanted to say before I return you to the recording of the tutoring session. I said before that I think that most chemistry classes won't give you two sample problems, won't test you on two sample problems where the water changes phase. But now that I think about it, that wasn't quite right. What I should have said is most courses won't give you a two sample problem where the water changes phase and you have to find the final temperature, like this. So two sample problem. The question is asking you for the final temperature. Water changes phase. I think this is generally not going to be tested. You might actually see some problems like this on your homework, but those problems are hard enough, they're usually not going to be on exams. So even if you do see some problems like this in your homework, they probably won't be on the exams. On the other hand, to complicate matters, you might see a two sample problem where they're asking you for the mass of one of the samples. If they ask you for the mass of one of the samples, then maybe the water will change phase. You might be tested on this. But that's okay because these problems are not as hard as these problems. If they're asking you for the mass, that means they would have to give you the final temperature. So in these problems, you would be given the final temperature so that you can figure out the mass, and then you wouldn't have to guess, would you, which region we're going to end up in. If you're given the final temperature, then you'll know whether the water is changing phase or not. And then you can use the methods that you've seen earlier in these videos to deal with those phase changes. Later on in this video series, we will do some two sample problems that ask you for mass. The problems that we do, I don't think involve water changing phase, but it shouldn't be too hard for you to adapt if you did see a two-sample problem that asked you for the mass given the final temperature where the water did change the phase. All right, well, I don't know whether what I'm saying here is making sense to you or not, but anyway, I tried to clarify the issues here. This type of problem might appear in your homework, but it usually is not tested in chemistry exams, which is good because we didn't do any problems like this in this video series. This type of problem you might actually be tested on. We didn't do any problems exactly like this in the video series either, but we did do some two-sample problems where they ask you for the mass and the water doesn't change phase, and I think you would be able to adapt that to the other types of problems. You don't need to do the guessing strategy here. These problems are easier because you don't need to guess what region you're ending up in because you would be given the final temperature. All right, let's try number 1 here.
200 grams of silver at 350 degrees Celsius are mixed with 200 grams of water at 30 degrees. Find the final temperature. Okay, well, we know that 200 grams of water. Okay, well, we know that they're looking for TF. And we know that we have 20 grams at 350 and they're mixed with 200 grams of water at 30. So then the temperature of the water is going to change, is going to increase, which means that the Q's that we are going to get should be positive. So we know that our initial starting temperature of water is at 30 degrees C in the liquid phase, and then it's going to increase somewhere up on the heating curve. I don't know where exactly. And then with the 20 grams of silver, our initial starting point is at 35 or 350 degrees C. And the final temperature is going to decrease somewhere. It's the final temperature will be in between 35 or 350 and 30 degrees Celsius. So then we can set up our equation. 0 is equal to, since the first step is temperature or specific heat involved, that is equal to M1 C1 delta T1, or actually TF minus T initial plus M2 C2 TF2 minus TI2. Now that means that 0 is equal to, we have 200 grams of water times 4.184 times TF minus 30, and then plus 20 grams of silver times 0.129 times TF minus 350, 200 times 4.184, so now we get 0 is equal to 836.8 times TF minus 30, and then plus 20 times 0.129 is equal to 20.129.
All right, let me catch up with you here.
Times TF minus 350.
Let me catch up with you here. So let's see. You have here you have 0 equals what?
0 is equal to 200 times 4.184 times TF minus 30 plus 20 times 0.129 times TF minus 350.
Where did you get that 0.129 from?
The gold.
And where did you get the gold from?
Oh, whoops, sorry. It's actually silver.
Okay.
So then silver is 0.240. So it's actually 20.240.
You said 0.240? Yeah. So silver is different than gold. 0.240 is the specific heat for silver. Good.
Right. So now we can distribute. So 0 is equal to 836.8 TF minus not 2030. 836.8 times 30 is 2,500 So 836.8 TF minus 25,104 plus 20.240 TF minus 350 times 20.240, and that's equal to negative 7,084. Now we can combine like terms, so 0 is equal to let's
make sure that we haven't made any mistakes so far. So what's the latest equation you have written down?
So 0 is equal to 836.8 TF minus 25,104 plus 20.240 TF.
Wait. So 25,104? Ah, right. So it looks like maybe I made a mistake. So that should be 25,000. Yeah, you were right. All right. And then plus what? I just want to make sure we...
4.8.
Times TF, and then...
Minus 7,084. Sorry, oops. It's 4.8 times 350. 1,680.
Okay, so is this what you have written down now?
Yeah.
Okay, so now what?
So 836.8 plus 4.8 is 841.6 TF minus 25,104. Minus 26,784. So 26,784 is equal to 841.6 TF. So TF is equal to 31.8, so 32 degrees Celsius. And that matched our prediction.
Yeah, that matched your prediction. Now remember, you were just guessing that the final point would be here. It's also possible that the final point might be here, or here, or here, or here. How can you tell that your guess was correct? Because the temperature came out to be between 30 and 100. If the temperature had not come out to be between 30 and 100, that would mean your first guess was wrong, and you'd have to take a different guess and try the problem all over again. But in this case, that turned out to be right. That was a fair guess because, again, it's much harder to change the temperature of water than of silver. And also, we started out with much more water than silver. Since we started with much more water than silver, we would expect that the water's temperature would change much less. Okay, now what's the very first equation you wrote down? So the way to do this to be systematic is to recognize that we have two heat exchanges here. Here's Q1 and here's Q2. One heat exchange for the water and one for the gold. So I would recommend that this should be the first equation you write down. This nice general simple equation, and then we can, then we can start plugging in. And notice we don't need a different symbol for the two final temperatures because the two final temperatures are going to be the same. So we can just call it T final instead of calling it T final 1 and T final 2. Okay, that looks like that was correct. All right, so we've done two different types of problems. We've done one sample or one substance problems, and we've done two sample or two substance problems. What is the first general equation you write down to solve a two sample problem?
The first one would be 0 is equal to Q1 plus Q2.
Or in general, if there's more than one heat exchange, you would write down this. The sum of the heat exchanges equals 0. That's how we just solved the last two problems. Now, earlier we were doing one sample problems. Can you think back, what was the very first general type of equation we wrote down for doing one sample problems?
Q total is equal to Q1 plus Q2.
Or just the sum of the Q's, because there might be more than one. That's right. So it's important to watch out for there. Now there's two different types of problems we've learned how to do. Now these two sample problems were also thermal equilibrium problems. Notice that the problem we just did didn't say that they were reaching thermal equilibrium. You're just supposed to assume it. If there's two different samples, you're just supposed to assume they're reaching thermal equilibrium. Now, notice that there's one sample, it can't be a thermal equilibrium problem, because what does thermal equilibrium mean? Thermal equilibrium means that the two things reach the same temperature. If there's only one thing, there's nothing for its temperature to equalize with. So here, the Q's don't have to add up to 0. Because here we have a single thing that's losing or absorbing heat to the environment. Here we have one thing that's losing or absorbing heat to the environment, so the Q doesn't have to add up to 0. But if you have two different samples, we assume they're insulated from the environment. So their Q's add up to 0. So that's one thing to watch out for.